Hi folks, welcome back to Physics with Captain Rod. I'm making this video to help you along with number 30 here in your Unit 2 homework. What a nice looking picture, if I do say so myself. Okay, so let's chat about this system here. We got this 20 kilogram mass and this 50 kilogram mass. And when you start thinking about these different problems in physics, keep in mind, all right, that at this point in the class, we've talked about 3 different types of physics. And you want to be kind of mindful about what it is you're trying to do or what you're trying to apply. All right, the first type of physics we talked about in this class was the study of motion, basically. And usually what I focus on is the ability to describe the velocity of a system with some sort of graph and use concepts of slope and area to talk about acceleration and position. The second type of physics is Newton's second law, and this means drawing free bodies and writing what I call Newton's second law equations, sum of all forces equals mass times acceleration. And the third type of physics is principles of work and energy. And these are 3 distinctly different things. So be very mindful, when you're working homework, which one you're using, which one you're trying to apply. So in this particular problem, this mass here, and although I guess it doesn't say it, but this was definitely assumed to start from rest. And it hits the ground, and it accelerates down. It covers that 4 meters in 9 seconds. And the first question here is to draw a velocity graph, find the final speed. Now, this one actually gave you the directions. Let me talk about the number 1 mistake I see in problems like this. You cannot just take the 4 meters, divide by 9 seconds to get the final velocity, all right? It's very important to realize when you do that, what you're calculating is an average velocity, not a final velocity. Now, there's a couple of ways you can use that, though, right? That doesn't mean you haven't done anything of any value here. I'm trying to, get this to allow me to scroll here a little bit. Let's turn it. Come on. There we go. Start by drawing a velocity graph. And if you just do down positive, you're going to have a coordinate, it's going to look like this and this. And the time you don't know and the v final, let's go back. The time you do know, the time was given in that problem. It's the v final that you don't know, and that's this distance right here on the graph, okay? And remember that the change in position, in this case it's a change in y of 4 meters, right? That relates to this graph. That should allow you to write a pretty simple, easy equation to calculate v final. Now, there's another way you can get the v final, and it's a way I tend to not use a lot until a little later in the course, but anytime your velocity graph is linear, right, so velocity against time, I usually recommend people, use this trapezoid approach. Now, if you think about what you're doing when you do that, when you take left plus right, divide by 2 times the time, these are velocities here and here. And what you're doing is you're calculating the average velocity. So when you say the change in position is equal to the area and you calculate it this way, this quantity is the average velocity. And notice you can get that by taking your initial plus final and dividing by 2. This is true anytime the acceleration is constant. And that will make a lot of these problems pretty short. See, if we go back to this one, if you take the delta y here and calculate by the delta t, you're calculating this, the average velocity. And if it starts from rest, that should give you an idea what this is, and it makes it pretty easy to solve for v final. Now, the reason I don't focus on that approach is because this is only true when your velocity is linear. Okay, when you got this case. Whereas my approach of using area is always true. Always, always, always. So I like things that are general and robust. But anyway, in any constant acceleration problem, your velocity graph will be linear, and you can use this type of approach to get your v finals. So that should get you by the first part of the problem. It's probably more than you needed, actually. Part B, use principles of work and energy to find the force of friction acting on the 50 kilogram mass. So what you're going to do, all right, is remember, draw the system at position 1 and position 2. That's a requirement for your work, for any work energy problem. Go through the PE1, the KE1, the PE2, KE2, and the work term. And again, the work term is the one that's going to take a little discussion here. As this system moves, all right, you've got a gravitational force down here, no doubt, and ask yourself, does that force do work? Is question number 1. And if the answer is yes, then ask yourself, have you already taken it into account in your work energy theorem? Ask that next, right? And if you have, you don't need a work term for that. The tension is an internal force and doesn't really need to be worried about. Even if you tried to do a work term for the tension is up on this object. So as it moves down, as the object moves down, the tension's doing negative work. That same tension acts here on this object, and as that thing moves to the left, the tension does positive work. Even if you try to include it, you're going to end up with a network of 0. Okay, other forces acting on the system to consider. There's really a force acting on the pulley here. You probably wouldn't realize this. I'll go ahead and give you this one. You don't need to worry about any sort of work down there. And the reason work is force times distance, but the pulley never moves. The spot where that force is applied never goes anywhere, so there's no work done there, no problem. You got gravitational forces over here and normal forces to consider. Hopefully the answer to that is obvious. There's one more though, a frictional force at this surface. So that one will have to be taken into account in your work energy equation for that problem. So that should be enough to get you through this problem. I'm going to go ahead and call that a day there. I hope that this video helps. Have a great day.